So as Zorza said, I'm a fifth-year graduate student working. I have three PhD advisors, one mainly at George Washington University, which is Krista Kugliotu, and then I also work through the University of Maryland College Park with Nora and Brad Senko. This work today that I'll be discussing is essentially half of my thesis, which is on the host galaxies of short GRBs. The other half of my thesis with Krissa is on a galactic plane survey with Swift XRT focused on high mass X-ray binaries and magnetars. But I'll focus on the short GRBs today. So first, I'll give like an introduction of what is short GRB is, and why we care about their host galaxies, because I know that some of you work on GRBs, but I'm not sure if everybody does. So a short GRB, can you hear me?
Tim.
Yes.
Okay.
Can you unmute your microphone, please, Brendan?
Sorry, have I been muted the whole time?
Just
No.
Okay, sorry. I thought somebody was trying to talk to me for a second, so maybe that's when it happened. Okay, sorry about that. So starting again with what a short GRB is. So a short GRB is defined as a gamma ray emission lasting for a duration of less than 2 seconds. This emission is followed by a longer lasting radiation across the electromagnetic spectrum from radio to gamma rays. And this is caused by a relativistic jet decelerating into its environment, into a dense environment. One of the reasons for this talk, why we care about the afterglow, is because this allows us to pinpoint on the sky where the short GRB is actually happening, which is important if we want to localize it to a specific galaxy. So the reason we care about short GRBs is because they are caused by the merger of two neutron stars, and because of that, they're relevant to modern astrophysics in terms of being a gravitational wave source. So on the right, we see the connection between gravitational waves and binary neutron star mergers and short GRBs. We have the gravitational wave in spiral signal, and then about 1.7 seconds later, we detected a short GRB. And then from that location within the host galaxy, we identified the electromagnetic counterpart. And essentially, this is why we care about short GRBs and their environments, because it tells us where we should look for gravitational wave sources, because the localization error boxes are very big. And in order to find them, we have to preferentially target the right type of galaxies. So just going into why we care about the galaxies even further. So one of the reasons is that short GRBs are very faint in the optical. And the way we actually find the distance scale and the redshift of these events is by their galaxies, because optical spectroscopy of the specific afterglow has only been measured for a short GRB about 4 or 5 times. And the other 40 short GRBs with host galaxies, all of their redshifts come from the galaxy itself. So we see here that they actually have a very diverse environment. These are 2 GRBs, which are found at very similar redshifts, but have very different host galaxies. One is an early type galaxy, and the other one is a late type galaxy with ongoing star formation. But in fact, the short GRB is not being found coincident with the star formation, and is even actually found outside of the light of its galaxy by a few kiloparsecs. And this is really one of the main predictions of binary population synthesis for neutron star mergers, is that at the formation of the binary, there's a supernova explosion, and that ejects some mass. And due to conservation of momentum, these systems can get kicked sometimes up to a few hundred kilometers per second. And because of that, over the time it takes between formation and merger of the binary, they can travel great distances. And this is one of the other things that makes the host galaxy important, is because it tells us how binary neutron stars merge, and provides insight into the amount of ejected mass and what kind of supernova explosions could actually be causing this. How do these systems actually evolve? And in both of these cases, the spectroscopy is of the galaxy itself, not of the GRB. So in order to actually get a distance, we need to find the right galaxy. And one of the main questions that I'll be talking about here is, what is the right galaxy and how do you know? Because picking the wrong galaxy for the GRB will change the distance of the event, affecting our understanding of its energetics. which has implications for a lot of different factors going forward in the population. So the main focus of the study was on hostless short GRBs. So these are GRBs where we do not see a galaxy coincident to the localization. And this is actually the case for about 30% of the population, despite very deep observations. So we see here a Keck R-band image of GRB 130912A. The optical localization is shown by magenta, and we do not have a galaxy underlying this. Instead, there's a candidate host at larger offsets. But the probability that this is actually the host galaxy is very low. The probability it's just a random galaxy on the sky at this distance is about 20%. And because of that, we could not consider it a robust association. And this is the case for many of the hostless events. There are always candidate galaxies, but whether or not it's the right galaxy is another question. So how do short GRBs get to large offsets? And I talked about this kick velocity following a supernova, and we have to consider that the time delay between formation of the binary and merger can be up to 10, 13 billion years. It can be a very, very long time. And even a kick velocity of about 15 kilometers per second would allow you to move very far distances. So if this kick velocity the binary gets is greater than the escape velocity of the galaxy, then this system can actually go and move into the intergalactic medium, into a very, very low density environment. And I would consider this a physically hostless GRB. So there's two main definitions. There's a GRB which is merging in its host galaxy, as we see here, merging within the light. It's on an elliptical orbit at first, and eventually it merges at, most likely, the furthest distance that it can in its orbit. And in this case, it's within a galaxy, but if we can't actually associate it to that galaxy because of, it's too faint or it's at a large distance, then we'd consider it observationally hostless. It's still actually within a dense environment, and we can know something about the densities environments based on their afterglows. But if this event is actually kicked really, really far from its galaxy and occurring in the intergalactic medium, then we would call it physically hostless, meaning that it has actually escaped its host. And in that case, associating it to a galaxy is almost impossible. So the two main scenarios that explain these events are, as I mentioned, a large offset from the galaxy, or that it's at a really faint galaxy and at high redshifts. So we see here a very interesting example that just came out from Aguay Fernandez et al. 2021. And here's the optical localization. And we see that there's nothing here. And the limit on this galaxy is the deepest for any short GRB host galaxy. It's 27.2 AV magnitude. And I'll show another plot where it emphasizes how deep that is compared to the rest of the population. But the most interesting thing for this event is that we know it occurred within a dense environment. And we know that because this is actually one of the few cases with optical spectroscopy of its afterglow. At about 8 minutes after this event, the VLT X-Shooter instrument was able to take a spectrum and find Lyman alpha. And this Lyman alpha break gives the redshift of about 1.7, the second highest redshift for any short GRB, and tells us that it occurred within a very dense environment, yet we are not seeing the galaxy. So this is the best case for a high redshift population of missed hosts. And of course, if there's a higher redshift population, it tells us that short GRBs could actually be the main cause of our process nucleosynthesis and populating the early universe with heavy elements. Whereas if they're really a lower redshift population and dominated by low redshift things, then that might not be the expectation. And this is one of the main things that we can take away from observations of short GRBs and what their redshifts are. It's also important because if they are occurring at large offsets, if we consider, an event at 40 megaparsecs, if it's 200 kiloparsecs away from the center of that galaxy, because it got kicked really, really far on the sky, that's almost an arc minute, and that makes it really hard to associate it to the correct galaxy following a gravitational wave trigger. So we need to know what the typical distance these events are occurring at. So now I'll discuss the sample selection. So essentially, 30% of short GRBs do not have a host galaxy. This is not even considering those that are hostless. The hostless fraction is only 5% of the overall 130 short GRBs detected by SwiftBat. So to select our sample, we started on the right, you see a schematic. We have about 130 short GRBs from SwiftBat. We apply some selection criteria to these events to sort some out, just to make sure that our search is meaningful. That these GRBs are localized to a good enough region on the sky where we can actually say what the true galaxy is. And then we carried out late time optical imaging with the Lowell Discovery Telescope, Gemini, Keck, HST, GTC, and a variety of other instruments. And this campaign with at least the Lowell Observatory has been going on since 2014, and well before I actually joined this project. So it's an extensive project going back many, many years. And if we detect a galaxy in these observations, then we'll try to characterize its spectrum through spectroscopy, or if it's too faint for spectroscopy to get a redshift, we will actually try to get multicolor imaging and then derive a photometric redshift for the event, just so we can still find out what the distance scale is. But if there's no coincident galaxy, that's when we went and used Keck and Gemini and these larger aperture telescopes, because to identify whether or not there's a faint host underlying the GRB position, we need very deep imaging. So our final sample of events that we actually were able to target is 31 of them. And this doubles the sample of well-studied events. So previously to this study, there was only about 45 events with host galaxies known. And now we're improving on that sample. 14 of these events we targeted only have an XRT localization, while 17 have a subarc second localization from optical or radio or Chandra. 6 of the events in our sample display extended emission. And overall, we are analyzing about 150 observations covering the optical to infrared wavelengths. So about 5.
Brandon,
yeah.
So I probably missed your explanation. So what was the difference between hostless and no host?
Yes, let me go back. So hostless at this point, it's not clear whether or not it does or does not have a host. So it's a little bit complicated. So for this specific event, we can say there is not a galaxy directly underlying this position. Okay, but there are other galaxies nearby. And say we didn't know the redshift of this event, then we would calculate what is the probability to find the galaxy of this brightness or brighter at this distance from the GRB localization. And that will tell us whether or not the association is likely. In this work, we require that the probability that this is just a random alignment on the sky is less than 10% for it to be a putative host galaxy. But if that value is greater, then we would consider it a hostless GRB, because we cannot say what the galaxy is or whether or not it was actually occurring in a faint mist galaxy or one at large offsets. Does that answer the question? There's a sort of this caveat between whether or not it's actually doesn't have a galaxy or whether or not we just can't tell what the galaxy is based on our observations.
Okay, all right, thanks.
Okay, so here's some examples of short GRB host galaxies taken from the Lowell Discovery Telescope. So we see here, this one has an XRT localization. It's quite big. This one has an optical localization. So in this case, just going back to the question, in this case for 140129b or 170728b or these other ones where the galaxy is just right on top of the optical localization, we do know there's not going to be any other more likely galaxy. That essentially has to be the host galaxy. But if we look at 140622a, in fact, there's a large XRT localization, and the most likely galaxy to be associated to it at 0.96 redshift is located outside of that localization at some larger offset. And we have to consider why G1 is a more likely host than G2. And this just has to do with the probability to find a galaxy of that brightness randomly on the sky. So out of these 31 events, we find 18 have host galaxies. We find a spectroscopic redshift to 7 of these events and a photometric redshift to 8 others. So we've definitely improved on the number of short GRBs for which the distance scale is actually known, and doubled the sample of XRT localized events with hosts, because previous work has only focused on those with a subarc second position. So in total, out of our work plus the literature, there's 72 well-studied events, 52 have a host galaxy association, and 20 are observationally hostless, because we cannot tell what the true galaxy is or whether or not there is actually no galaxy at all. And that's about 30% of the population. So going back to short GRBs again, just to emphasize it, I think I actually talked about this enough, so I'll skip this slide for now. So now we can talk about population characteristics just of the total 72 events, not just the ones within this sample. So if we look at a plot of R-band magnitude versus redshift, we see that all of these galaxies are sort of tracing the brightest galaxies at each redshift. So these black lines mark 0.1 to 1 L-star galaxies, which are essentially the brightest galaxies at each of these redshifts. And short GRBs are preferentially forming in these massive galaxies about 10 to the 10 solar masses, sometimes up to 10 to the 11. But of course, as we go out in redshift, just because of distance, these events become fainter and more difficult to detect with ground-based observations. And in fact, here is the event for GW170817 which we know is at a redshift of Z of 1.7, and this is an upper limit on its host galaxy. So this is the faintest galaxy found for a short GRB, and a very interesting case of a GRB that has to have a host because it was found in a dense environment, which we know based on Lyman alpha, but for which we do not find the host. And of course, deep HST observations in the infrared are going to be really important to find that galaxy and characterize it. So these purple diamonds are actually galaxies that are candidate hosts for the, so the probability of association to the GRB is greater than 10%, but these are galaxies nearby to these GRBs we can't find a good association for. And we find that all of these are actually occurring at very faint magnitudes, which based on these black lines would put them at about Z of 1 or higher. And this is interesting because this is sort of an evidence for a population of galaxies that are at Z greater than 1, but cannot be associated to the GRB just because of their faintness and because the event may have been kicked to a distance of about 25 kiloparsecs. And if we consider these events, these galaxies as being a lower redshift thing, they had to still be at Z greater than 0.5 to explain this gap here. Because if these were low Z events, then there's no reason why we would not be identifying their host galaxies. It's a weird thing to not see this gap between 22 to 24 if there are indeed galaxies that are much fainter than this. So we take this as a sort of selection bias against high Z events. So here we have the R-band magnitude versus the angular offset from the GRB. And this gray shaded region gives us a probability of chance coincidence greater than 10%. So this is the gray region are those for which, regardless of whether that galaxy is the true host, we cannot say based on the typical arguments used to associate them that is the galaxy, that is the true galaxy. So this is just the region where we don't know and we can't really say anything about it. But we find that all of these ones typically that are being found in this region are typically faint. And going back to this plot, we see here that about 24 magnitude, something below 24 magnitude is very likely to be at a high redshift, greater than 1, okay? So if we consider that and we say, okay, here's 24 or 23.5, and we draw a line over, then we see that at Z greater than 1, the distance to the galaxy has to be less than 3 arc seconds in order to say that is the galaxy. That is the true host. It has to be less than 3 arc seconds, which at Z of 1 is about 25 kiloparsecs. So it's not unexpected that we're finding a population of events at greater than 25 kiloparsecs that are faint, for which we can't say it is the true galaxy, because just due to their faintness, it's not possible to draw this association. So now I'll talk about sort of redshifts and offsets and what those distributions look like. So the observed redshift distribution is shown here with the number of events versus redshift. We have spectroscopic redshifts in purple and photometric redshifts in blue. The so-called redshift desert, where typical signs of star formation and emission lines are shifted out of the optical and into the infrared, is shown. So that's essentially a region where we can't really probe spectroscopic redshifts very easily, and it becomes much more difficult to find them. So up until the past few years, maybe 2017 or something like that, there was no short GRBs out here. These are all very recent events at high redshifts, and maybe that's due to improved sensitivity or improved capabilities of what we know we have to do to find these events now that we know they might exist. You know, how deep do you have to go with your instrument, and how do you have to look for them? But that's an interesting thing in coming years to see whether or not this continues to build up, or whether or not we still see the majority of them coming at lower redshifts, and if that is a selection bias or not. So if we look at the cumulative distribution of redshifts, which is the black line here, and we compare this to different distributions for the time between formation and merger of the binary neutron star system, we see that these are sort of disfavoring some of these models. Like these models that are sort of older are predicting almost no events at z greater than 1 for the reason that I just said. These are newer events that are being found. So more recent modeling is actually finding that a power law distribution of delay times is more likely and favored. And this is essentially saying, okay, the time between formation and merger can be much smaller than was previously thought, which is interesting because it tells us there's a higher redshift population. So if all of these galaxies that were the purple diamonds in my other figure are at z greater than 1, and these are the true associated ones, then that's shown by this dotted line here, where in this region we have essentially a lower limit. And this also begins to really disfavor these other models. So we'll see in coming years as we get more redshifts and also more gravitational wave events, how this distribution starts to change. So now I'll talk about the offset distribution. So this is the distance to the GRB from the center of the galaxy is what we're measuring here. And in this work, it's this red distribution, whereas in older paper from Fong et al. 2013 is shown in black. We see that the red and black lines are very similar. So although we're adding another 20 events to this figure, the distribution of offsets is pretty similar. And 70% of them are still at less than 10 kiloparsecs with a median at about 5. But we do still see this tail of events that are going out to almost 100 kiloparsecs offset. And these are really difficult to associate events because at a large distance, it's hard to say it's the true galaxy that you're finding here. So now that we have 72 events to look at, as opposed to like 40 before, we can start to split these distributions in redshift. And if we take the offsets for subarc second localized short GRBs and we split them at a z of 0.5, so the lower redshift population is in blue and the higher redshift is in red, we see that there's actually a difference here. And in fact, there's none of these high redshift events at greater than 15 kiloparsecs. And this could just be due to the fact that because the galaxies at those redshifts are faint, it's harder to associate those at larger offsets to them, just based on the way we calculate the probability of associating galaxy. The other possibility is that this is a true physical effect, that we are seeing an evolution in the redshifts of short GRBs and their progenitors in terms of their galaxy, as well as the distances that they can actually reach when they get kicked. And of course, we'll have to see whether or not this continues to be the trend, and what the true effect is, because at this point, it's not really clear whether or not it is a selection bias or a redshift effect. It needs sort of more study. So if we normalize these offsets by the galaxy. So essentially that means the offset is the distance between the center of the galaxy and the GRB. If we divide that by like the size of the galaxy, that's what this figure is showing us. So it's in units of half-light radius of the galaxy. And we see here's our distribution in red, and here's the median for long GRBs. So again, still we're finding that the median between short and long GRBs is a factor of 2, with long GRBs being found in star-forming regions near the center of their galaxies. And this is, again, a good indicator that these are separate populations, which prior to 170817 was the best evidence for that. So here we can look at offset versus galaxy type. Here's a histogram, projected physical offset in kiloparsecs. Late type spiral galaxies are in purple, and elliptical early type galaxies are in green. We see that the large offsets are mainly dominated by early type hosts at low redshifts. An example, which is this furthest one out here, is 090515, where we see G1 here is a very bright elliptical galaxy at a redshift 0.4. The distance to the GRB localization is 14 arc seconds, which corresponds to 75 kiloparsecs at that redshift. And this is one of these events which, you know, you can see how do you pick what are the true galaxies, right? You have many galaxies in this field, and in fact, there's one much closer to the GRB position. But just due to the brightness of this one, it's more likely to be associated. And this I think is a really nice figure that shows exactly the difficulty in finding the host galaxies of short GRBs that are kicked to large distances, just based on how many galaxies there are in the sky. So if we look, so I mentioned earlier that hostless short GRBs, we'll just go back here. So this GRB, this galaxy here, the probability that it's just a random alignment on the sky is, I think, about 15% for this event. So actually, this is one of those that could be considered hostless, despite there being many likely galaxies in the field. And the way we take, so essentially in the next slide, there's a sample of other things like this, where there's a galaxy, sometimes it's this one, sometimes it's further, and we're taking the galaxy that's most likely to be associated to the GRB, even if it's a little bit above our cutoff threshold, and we're saying, what is the distance to that? So if we do that, we find that the hostless events shown by this blue line in the cumulative distribution function are actually all being found at large offsets. It's not unexpected. In order for them to be hostless, they have to be well outside of the galaxy's light. Otherwise, they would be the obvious choice. And so it's a factor of 5 times in difference between those with hosts and those who are hostless. And so either that's the true scenario, and all of these, like this event, are the correct galaxy and the correct redshift, or there's a missing population at high redshifts that we're just not seeing, that should be exactly coincident with these galaxies. And I'll show some other examples of this next, where with ground-based observations, we do not see a galaxy coincident, but as soon as we look with HST, I mean, very deep imaging, 2 or 3 orbits with HST, in the infrared, we do see a galaxy. So, you know, all of these that are only observed with ground-based observations need to be observed with HST and JWST to prove that there is not a different galaxy at high redshifts. So here, this was the original one I showed, where with Keck, which is, you know, the best we can do from the ground, there's nothing here. But if we look with HST in the infrared, we see there actually is a candidate host here that's very faint and likely at Z greater than 1. And this is just one of those cases where we need these space-based observatories, and emphasizes the importance of them, but also in not jumping to conclusions that this is the true galaxy just because it's the only galaxy nearby. Here's another case for GRB 090305A. If we see here, I mean, HST is resolving a number of galaxies in the field. This is another galaxy, but because this one's so much closer, it is the more likely host, and the one which in the literature is considered the correct one. And, you know, HST is very sensitive. It's more sensitive than the ground, but also looking in the infrared is very important, because the R-H color for short GRB host galaxies has a median value of about 2, Of course, there's a lot of scatter because they're found in both early and late type galaxies. So it becomes more difficult to say exactly what you would expect the color to be. But this is sort of what we're seeing based on these images. So the conclusions, 28% of short GRBs lack a host galaxy. So our work agrees with previous work from 2013, even after doubling the sample in terms of both the offset distribution and the fraction of those for which you cannot find the true, like very easily to assign galaxy. The other thing is we have discovered evidence for a selection bias against high Z events in the fact that there's not really an easy to explain reason for which all of the high redshift ones should be at smaller distances, besides that we cannot associate the true galaxy to those ones that are at larger distances. And in turn, we have identified a population of likely high Z galaxies that support this bias because they are those ones which would, if added to this distribution, make them look very similar. And that's everything that I have today. So any questions, I'd be happy to answer. I hope everything was clear.
It was very clear. Thank you very much.
Yeah, thank you.
Questions? Please raise your hand or open your microphone. Enrique, please.
Yes, thank you. I think it always helps me to hear these talks to clarify a little bit what's going on with the observations and the relationship with galaxies. But there's something that still is not clear to me what's going on with that, which is so we know that there's all these sort of very faint satellite galaxies, for example, to the Milky Way.
Okay,
and have, I think, reticulum 2 or one of those, which seems to have some R process enrichment.
Yes.
And if the source is not a collapsar, but rather, so not a long, but a short GRB, then a very tiny galaxy with very little gravitational was able to hold one of these events.
Yeah, yeah.
Now, I think Andromeda, for example, you don't necessarily see already those satellite galaxies because they are quite faint. Yeah. So I guess there would be no hope to find the host galaxy for anything which is even our satellite galaxies are not all well known from what I understand.
So this is a good question and very relevant. Of course, there's so many different avenues which I could have talked about regarding host galaxies, but I'm glad you brought this up because I think it's an important one. Yes, so there are evidence for our process nucleosynthesis in nearby dwarf galaxies, which are very low mass, make like maybe 10 to the 5, 10 to the 6 solar masses. That's a factor of 10,000 smaller than where we typically find short GRBs. So, there's one of the things that you would have to explain is how are these forming in much lower mass galaxies where there's just less stars and it becomes less likely to make a large number of neutron star binaries. The other question is, well, if these things are getting kicked to really large distances, then wouldn't they escape such a small galaxy if they can escape very large ones? And I think the best explanation for this, in my mind, is that binary neutron star mergers do not have to receive large kicks. And I know I've talked about that a lot in this talk, but if we think about galactic neutron star binaries, those actually have a median kick velocity of about 15 to 30 kilometers per second, which is much, much, much smaller than that of isolated pulsars, which have a velocity about 400 kilometers per second. And when people talk about large kicks in binary neutron star systems, they're taking the values for isolated pulsars. I think in many cases, we need to start considering these galactic binary neutron stars as being, relevant, especially to what you're talking about in terms of escaping these dwarf galaxies. The other thing is that Yeah, so the way that you could explain this and have them all be the same population is if you have a population of high Z galaxies that are actually coincident. So if we continue to find events like this for those for which we would have typically have said, oh, it's at a large offset, it had a large kick. If we continue to find these types of events where the kick does not have to be large, this would provide even further evidence for what you're talking about and for these small kicks and the ability to retain binary neutron stars in dwarf galaxies. The other thing I would mention is if we look at this plot, we see that short GRBs are tracing very bright galaxies, which are very massive. And when people do population synthesis models, we find they preferentially form within these very massive galaxies. So it would also be a challenge to explain it from that avenue. But then we have events like 160410, for which the galaxy has to be less than 10 to the 8th solar masses. And, you know, who's to say it didn't form in a dwarf galaxy? The point is, we may not know, but I don't think you can rule it out conclusively.
Right. So yeah, yes, I agree with several of the points you're making there. I think in a sense, so when you form one of these objects, you get actually 4 different kicks. You get the 2 and you get the 2 Blau-Boersma kicks.
Yeah.
So all of those can count. Now, if you already have an object that merged, you know that that binary remained bound. So the mass loss has to be rather small, or you have to be very lucky with those, with the alignment of those kicks.
Yeah.
However, I would guess that the preferred mechanism probably involves an electron capture supernova in at least one of them, if not in both of them. And that brings down the kick velocity much smaller. So in a sense, you could probably, I don't know how much degeneracy in the parameters there could be, probably a lot. But if you can get some morphology of those galaxies, and if you know whether the satellite galaxies are in the same plane or not, that could give you some information also of those extended disks and whatnot of those galaxies.
Yeah.
And I have no, well, I really don't know how far those galaxies, those satellite galaxies can be, but would it make sense to make a study on, okay, so this is, I don't know, 5 disks away, so that would be perfectly within the satellite galaxy population of that galaxy or not? Or this is elliptical, so you don't expect them to have, what, I don't know, has something.
So that's going back to sort of like this figure, right? You're saying it has to be a certain number of radii of the galaxy away to be in that population, right? Yeah, I mean, I don't know specifically that people have looked at it for satellite galaxies. I know the work has been done to see whether or not they could form in globular clusters. There's been a lot of work on that. About satellite galaxies, I don't know. I think that the difficulty with satellite galaxies is, you know, we have a hard time detecting even massive galaxies at certain distances.
Right.
And finding satellite galaxies there is just never going to happen, right? It's,
no.
We'd have to find a low redshift one. We'd have to find a really conclusive low redshift event coincident with a dwarf galaxy. And that's where gravitational waves come in, right? We'd have to find an event that's favorable, like 170817, where we can pinpoint the counterpart and then see it's associated to some sort of dwarf galaxy. Until that happens, I think it's going to be really difficult to prove. Regardless of whether it's a good explanation.
Right. I would not expect you to detect the dwarf galaxies, but other than by probably the morphology, and it's within the region that you would expect to happen. But I agree.
I mean, even morphology is hard, right? For this one, it's sort of just a smudge. So I think what you're saying is totally important. And the one where you could be able to do that is for these lower redshift ones. Like if you go back to the very beginning of the talk, right? Let's see. Yeah, so if we go back to these ones, they're very bright. One could do such a study here, right? They're at lower redshift. They have a morphology that we can say something about it. it would have to be these low redshift events. But I don't think that anybody's undertaken that study to date.
Okay.
Yeah.
All right. Thank you very much.
Yep.
More questions? If not, I just have a little, just let me ask something, because we have a lot of students here.
Yeah.
Could you please explain why it's important to have the infrared emission of this signal, just to say that not just the optical, please.
Yeah. So essentially typically ground-based observations, and most of the observations that we used in this work to really go deep to look for the galaxy with Keck and Gemini were in the R band, in the optical. But if we're talking about a high redshift galaxy, there's actually this break that occurs at a rest frame of 4,000 angstroms due to the older stellar population. And essentially we have the light is essentially flat, but then below this certain wavelength, it drops off very, very steeply. And this is one of the things that's important about infrared observations, because for only until really high redshifts like Z of 2 or 3 is that break actually affecting the infrared. But for redshifts of 0.5 to 1, it's actually going to be above the R band, meaning that a galaxy would just appear fainter in the R band because this break is happening there. And I think that that's the main reason why infrared searches are important, because they're not affected by this break in the galaxy SED.
Okay. Other question, because it was in a private in the inbox. What's the difference between GRB with a spectroscopic redshift and one with a photometric redshift?
Yes. So the redshifts, either spectroscopic or photometric, is coming from the galaxy itself. So actually, we're on the right slide for this. Here we see a spectrum, optical spectrum taken of this galaxy, and we see these emission lines. And based on where these lines are, because of the redshift, they have shifted towards redder wavelengths. And since we can assign all of these to be at the same redshift, we can say they're all associated to this galaxy at a given distance. But a photometric redshift, essentially the way we would get that is if this galaxy is too faint for actual spectroscopy, we can still take imaging. So we could take imaging in the G band, say 4,000 angstroms, we'll take imaging. Then we'll take another image at 6,000 angstroms and another image at 9,000 angstroms and then 12,000 angstroms. And we build some sort of spectral energy distribution, brightness versus wavelength. And what we look for is this break I was just talking about. So if we see that the light is sort of flat and then it falls off at one point, that can tell us that that's the likely 4,000 angstrom break. And then based on where we're finding that, say we're finding it at 6,000, that means the redshift is about 0.5. And in this way, we can estimate the redshift without taking a spectrum, just using the photometry.
Thank you. More questions, comments, suggestions?